Good afternoon, my YouTube viewers. In this particular video, we're going to be talking about the odds ratio, and that's another measure of association. So the odds ratio is commonly used in case control studies to assess the strength of association between a binary outcome and a binary explanatory variable. So what we're going to do is we're going to write a program to prove the odds ratio. And in order for us to write the program, we're going to have to import two libraries that are going to be necessary for Python to execute the program. So the first library that we're going to import is NumPy is NP, which is a numeric library that creates NumPy arrays, it creates distributions, and it performs numeric calculations. And then from scipy.stats, we're going to import Fisher exact. So scipy is Python's scientific library, and stats is a statistical module within scipy. And Fisher exact is the model that we're going to be using, or the function. So what we're going to do after we have imported the libraries is we're going to create a contingency table. So the rows are going to be exposed versus not exposed, and the column is going to be disease versus no disease. So the format is exposed with disease, exposed without disease, and then not exposed with disease, not exposed without disease. So that's the format that we're going to use to create this contingency table. So the data equals NP array, brackets, and you got the first row is 30, 70, and the second row is 20, 80. And now we're going to extract the observed values. So A, B equals data 0, and CD equals data 1. So data 0 is the exposed group, and data 1 is the not exposed group. So data 0 is going to be row 1, and data 1 is going to be row 2. So now we're going to calculate the odds ratio for each group. So odds exposed equals A divided by B, and odds not exposed equals C divided by D. So A divided by B is 33 divided by 7, and C divided by D is 2 divided by 8, or 1/4. And then now we calculate the odds ratio. So odds ratio equals odds exposed divided by odds not exposed. So, and then we're going to perform the Fisher test to evaluate the statistical significance. So odds ratio, p-value equals Fisher exact data. Your p-value is a percentage. So now we're going to display the results of the contingency table. So we're going to display the data, we're going to display the odds ratio manual calculation, odds ratio Fisher's exact test, and the p-value of the Fisher's test. So the contingency table is what we've already discussed. So row 0 is 30 and 70, and row 1 is 20 and 80. So the odds ratio manual calculation is 1.714, and the odds ratio Fisher's exact test is 1.714, and the p-value is 0.14. And so the p-value is the probability, and if the p-value is greater than less than 0.05, then what you have to do is you have to go with the alternate hypothesis. So if the p-value is greater than 0.05, you go with the null hypothesis, which means there is not a significant association between the two samples. And then if the p-value is less than 0.05, then you say that there is a significant association between the two samples. So in this instance, because the p-value is 0.14, the p-value is greater than 0.05. So the result is the association between the two variables is not statistically significant. So that's how you carry out the odds ratio. And so this is going to complete this video. The next video we're going to be talking about regression coefficients, and I hope you decide to watch it.